Let's talk about quantization of electric charge. The idea that all matter is composed of tiny particles or atoms dates to the speculations of the Greek philosopher Democritus and his teacher Leucippus in about 450 BC. However, there was little attempt to correlate such speculations with observations of the physical world until the 17th century. Pierre Gassendi in the middle of the 17th century and Robert Hooke somewhat later attempted to explain states of matter and the transitions between them with a model of tiny indestructible solid objects lying or flying in all directions. But it was Avogadro's hypothesis, advanced in 1811, that all gases at a given temperature contain the same number of molecules per unit volume, that led to great success in the interpretation of chemical reactions and to development of kinetic theory in about 1900. It made possible quantitative understanding of many bulk properties of matter and led to general acceptance of the molecular theory of matter. Thus, matter is not continuous as it appears, but is quantized or discrete on the microscopic scale. Scientists of the day understood that the small size of the atom prevented the discreteness of matter from being readily observable. In this video, we will study how 3 additional great quantization discoveries were made: electric charge, light energy, and energy of oscillating mechanical systems. The first estimates of the order of magnitude of the electric charges found in atoms were obtained from Faradays Law. The work of Michael Faraday in the early to mid-1800s stands out even today for its vision, experimental ingenuity, and thoroughness. One aspect of his work concerned the study of the conduction of electricity in weakly conducting solutions. His discovery that the same quantity of electricity F, now called the Faraday, and equal to about 96,500 coulombs, always decomposes 1 gram ionic weight. That is, Avogadro's number Na of monovalent ions leads to the reasonable conclusion that each monovalent ion carries the same electric charge E, and therefore F is equal to Na times E. This equation is known as the Faraday's law of electrolysis. While F was readily measurable, neither Na nor E could be experimentally determined at that time. Faraday was aware of this, but could not determine either quantity. Even so, it seemed logical to expect that electric charge, like matter, was not continuous but consisted of particles of some discrete minimum charge. In 1874, Stoney used an estimate of Na from kinetic theory to compute the value of E from equation 1 to be about 10 to the negative 20 coulomb. However, direct measurement of the value of E had to await an ingenious experiment conducted by Millikan a third of a century later. Meanwhile, Peter Zeeman in 1896 obtained the first evidence for the existence of atomic particles with a specific charge-to-mass ratio by looking at the changes in the discrete spectral lines emitted by atoms when they were placed in a strong magnetic field. He discovered that the individual spectral lines split into three very closely spaced lines of slightly different frequencies when the atoms were placed in the magnetic field. This phenomenon is later called the Zeeman Effect. From his measurements of the splitting, Zeeman calculated Q over m to be about 1.6 by 10 to the power of 11 coulombs per kilogram, which compares favorably with the presently accepted value 1.759 by 10 to the power of 11 coulombs per kilogram. From the polarization of the spectral lines, Zeeman concluded that the oscillating particles were negatively charged. The year following Zeeman's work, Thomson measured the Q over m value for the so-called cathode rays that were produced in electrical discharges in gases, and pointed out that if their charge was Faraday's charge E as determined by Stoney, then their mass was only a small fraction of the mass of a hydrogen atom. 2 years earlier, Perrin had collected cathode rays on an electrometer and found them to carry a negative electric charge. Thus, with his measurement of Q over m for the cathode rays, Thomson had, in fact, discovered the electron. That direct measurement of E over m of electrons by Thomson in 1897, a little over a century ago, can be justly considered to mark the beginning of our understanding of atomic structure. When a uniform magnetic field of strength B is established perpendicular to the direction of motion of charged particles, the particles move in a circular path. The radius r of the path can be obtained from Newton's second law by setting the magnetic force QUB equal to the mass m times the centripetal acceleration u squared over r, where u is the speed of the particles. In Thompson's experiment, he adjusted perpendicular magnetic field and electric field so that the particles were undeflected. This allowed him to determine the speed of the electrons by equating the magnitudes of the magnetic and electric forces, and then to compute E over m from equation 2. Thompson's experiment was remarkable in that he measured E over m for a subatomic particle using only a voltmeter, an ammeter, and a measuring rod, obtaining the result 0.7 by 10 to the power of 11 coulombs per kilogram. Thomson repeated the experiment with different gases in the tube and different metals for cathodes, and always obtained the same value for E over m within his experimental uncertainty, thus showing that these particles were common to all metals. The agreement of these results with Zeeman's led to the unmistakable conclusion that these particles, called corpuscles by Thomson and later called electrons by Lorentz, having 1 unit of negative charge E and mass about 2,000 times less than the mass of the lightest known atom, were constituents of all atoms. The fact that Thomson's E over m measurements always yield the same results regardless of the materials used for the cathodes or the kind of gas in the tube was a persuasive argument that the electrons all carried 1 unit E of negative electric charge. Thomson initiated a series of experiments to determine the value of E. The first of these experiments, which turned out to be very difficult to do with high precision, were carried out by his student Townsend. The idea was simple. A small but visible cloud of identical water droplets, each carrying a single charge E, was observed to drift downward in response to the gravitational force. The total charge on the cloud Q equal to NE was measured, as were the mass of the cloud and the radius of a single drop. Finding the radius allowed calculation of N, the total number of drops in the cloud, and hence the value of E. The accuracy of Thomson's method was limited by the uncertain rate of evaporation of the cloud. In addition, the assumption that each droplet contained a single charge could not be verified. Millikan tried to eliminate the evaporation problem by using a field strong enough to hold the top surface of the cloud stationary, so that he could observe the rate of evaporation and correct for it. That, too, turned out to be very difficult, but then he made a discovery of enormous importance, one that allowed him to measure directly the charge of a single electron. The discovery that he could see individual droplets and that droplets suspended in a vertical electric field sometimes suddenly moved upward or downward, evidently because they had picked up a positive or negative ion, led to the possibility of observing the charge of a single ion. In 1909, Millikan began a series of experiments that not only showed that charges occurred in integer multiples of an elementary unit E, but measured the value of E to about 1 part in 1,000. To eliminate evaporation, he used oil drops sprayed into dry air between the plates of a capacitor. By switching the direction of the electric field between the plates, a drop could be moved up or down and observed for several hours. When the charge on the drop changed, the velocity of the drop with the field on also changed. Assuming only that the terminal velocity of the drop was proportional to the force acting on it, Millikan's oil drop experiment gave conclusive evidence that electric charges always occur in integer multiples of a fundamental unit E, whose value he determined to be 1.601 by 10 to the negative 19 coulomb. The currently accepted value is 1.60217653 by 10 to the negative 19 coulomb. And that's it for now. We hope that you have learned something in this video. Thank you for watching.